So the first one, 9 times 81. You've already had this before. We can put it in the same base, which is base 3. 9 is 3 squared. 81 is 3 to the 4th. And when you multiply like bases, what do you do to the exponents? Add them. So the very first answer should just be, it's on 3s. So the very first answer should just be 6. The second one, when I ask you logarithms, what does that mean? It means the same thing as exponents. So if I told you to find log base 3 of 9, that's a logarithm. Your answer is 2, which is what? Just an exponent, right? So that is the same thing. Logarithms are the same thing as just finding exponents. All right, we look at the next one. If I have log base 6 of 2x minus 3, and that's equal to log base 6 of x plus 2, then what? We know if the logs are the same, then the exponents have to be equal, because this is saying 6 to what power equals 2x minus 3. But that value is the same as 6 to what power equals x plus 2. So 2x minus 3 has to equal x plus 2. The exponent, all of this log right here is an exponent. And all of this on the right-hand side is just asking for an exponent, and the exponents are equal. So it's saying 6 to some power equals 6 to some power. The answer to those are the same, so the arguments are the same. As Eric said, you move the x over, move the 3 over. I believe you got 5. That does happen to be one that was on your homework assignment, I do believe. Yep, that happened to be 56 on your homework assignment. And then we talked about how you solve them with inequalities. With inequalities, we have log base 2 on both sides. The exponents, the one on the left is greater than or equal to, so we can set the arguments up that way. So 4y minus 10 has to be greater than or equal to y minus 1. You solve an inequality the same way you solve an equal sign, unless you divide by a negative or multiply by a negative, then you flip it. So you move the y over. You move the 10 over to the other side. And then you divide by 3. So it's saying y has to be greater than or equal to 3. But what was one of the things we talked about? You have to do. Check your answer. Now, checking your answer sometimes meant 2 different things. What they look at when they say check your answer, not only does it make it a true statement, but you've got to make sure that the argument is positive. It can't be negative. You still have to make sure that it doesn't give you a negative value in there. So if I put 3 in, this becomes 12 minus 10, which is 2. That's a positive value. If I put 3 on the other side, I get 2. It does say equal to. I have my equal sign. There's your answer. But you still have to make sure that you have that positive argument there. So that also happened to be one that was on your homework assignment. Now, I believe you told me there was a few that you could not see.
Yeah, 67.
67, you can't read. Oh, see information from page 514, and you do not have that. Yeah, you do. 514 you have. Maybe you just can't read the problem. A proposed city ordinance will make it illegal to create sound at a residential area that exceeds 72 decibels during the day and 55 decibels during the night. How many times as intense is the noise level allowed during the day than at night? 73 you can't read? Oh, darn, and that's when I thought you might be able to.
Like
73, using the definition of a logarithmic function where y equals log base b of x, explain why the base b cannot equal 1. Why can't it equal 1? Yep. Not saying this right here. Why can't the base be 1? Because if you look at everything we've said before, we've said that x has to be greater than 0 and b has to be greater than 1. Well, then why can't it be equal to 1? If that's the case, you get one to the y power is equal to x. X will always be 1. So if you look at what's going to happen with your graph with x always being 1, no matter what it is, when you look at it, do you get an exponential? Do you even get a function? No. X is just always going to be 1. I don't care what your y value is. X is always 1, and you get a vertical line that looks like that. And that really is not a function. A function says when you have a value for x, you should only have one value for y. So it'd be this. If I told you log base 1 and then I say x is 7. Well, 1 to what power equals 7? Nothing. Nothing. It says 1 to what power equals 7. Well, that's never going to happen. 1 to any power is always 1. So for that particular one, it is a challenge question. It's just that it cannot occur because your value would always be 1, which is it's not a function. Hopefully you were able to answer the ACT questions that were on there.
Yeah, 74.
74, you can't read it? Okay, let me look through. Oh, all right, so you can rule out 74 then, because you don't have that page.
I struggle more. Like, can you put that log into
76 could possibly make it there, but I don't know. I just lost the tip to my pins, so my pin's not even going to work. Okay. Now which one were we doing again? 76. What is the solution to the equation? Soon I get this to work. All right, guess I have to do this. Oh, 3 to the x equals 11. If you look at the very first option that you get, the very first option says x is equal to 2. Is that true? No. All right, the next one says x equals log base 10 of 2. Is that an option? No, probably not. If you type it in on your calculator, what do you get? Log base.
9.
You just typed in log base 10 of 2.
No, I put 2 to the log 10.
I just typed in log 10. It says this right here. It says log base 10 of 2, right?
Yeah.
So you could calculate that and figure out what that is, or they say that is equal to x, so you could take your calculator, hit your exponent key, and then right there type, and then hit your log key. I would type that in right there and see what you get.
9.
This gives you 9, not 11, so that's not true, right? And we know the first one was not true because 3 squared is 9. Let's look at the next one. You have log base 10, 11 plus log base 10 of 3. So what happens if you take 3 raised to the log base 10 of a, you get a big number. That does not work, right? So let's try the other one. What happens if you take 3 and you raise it to the, hit your exponent key. Did you hit your exponent key? Now hit the fraction key. And then you can type in, what is it, log, you don't even have to hit base 10. You could probably just hit log 11, because if you just use the log key, that's understood to be base 10. So log 11 and log 3. And if you type that in, what do you get? 11. And can I tell you this much? As I'm going to answer this first here. Never mind. I'm not going to, I'll just leave it at that. And it does say you have to use the table on 5:14. So your decibels. Now you have to remember another formula. What was that? L, which is your decibels, is equal to 10 log base 10 of R. So what is it during the day? 72 decibels. So as we were talking about when we were actually solving these problems, when we did whatever numbers there were, is that 50 or? It's in decibels. Is it 72 decibels? 72 decibels, and L is your decibels, which is your loudness. What did we do to solve that equation when we talked about, is it 51, 52? You divide by 10 first. So I divide both sides by 10 to isolate the log, and you get 7.2 is equal to log base 10 of R. So R had a value of 10 to the 7.2 power. Now, what is it during the day? Oh, that is the day. What is it at night? 55 decibels. So then you're back to 55 is equal to 10 log base 10 of R. So once again, you divide by 10 first. So now R is equal to 10 to the 5.5 power. That's like 13, 14, 15. Sorry, I was saying 51, something like that. All right, so now what do you do to those two values? You subtract them, and if you subtract them, what do you get? So how many times? 10 to the 1.7. Now, if you want that as far as an actual number, how many times? Take 10 and raise it to the 1.7 power on your calculator. Yeah, I'm just going to say approximately 50 times. That'll work. If you put those two squiggly lines, that's approximately equal to that.
My squiggly's over that squiggly.
So I'm guessing sometimes the application part of it is going to get some of you. And I talked about 54 in class and how I disagreed with that one. Hopefully you were able to sketch the graphs in on your calculator and describe some relationships between the graphs. What do you notice about them? I just disagreed with the answer in the book. 53 and 54, for those of you that were gone, and for those of you that might have missed it when I said it in class, if you were here on Friday, what do you have to worry about with 53 and 54? Yep, you got to make sure that that argument is greater than 0, because when you solve that particular problem, what is, I don't know, what's 54? If you change that to exponential format, you start with your answer so you don't have to worry about flipping your symbol. What's 1/3 to the 0 power? 1. So P has to be less than 1. But we said, what about this argument right here? What do we know has to be true about that?
It has to be.
Got to be greater than 0. So you take whatever is in that box. In this case, it's just P, and it has to be greater than 0. So you don't have to solve anything from there. You just say that P then has to be greater than 0, but less than 1, anything between there. If I say that it happens to be -2, yeah, -2 is less than 0, but there's no way you can get -2 because a positive base raised to any x to any power is going to be a positive answer.
What did 0 work? Because P, if you just put that in 0, that'd be.
That can't be 0 because 1/3 to any power does not equal 0. That the graph of that is always greater than 0. There'll never be an equal sign right there because the argument has to be greater than 0. Now we said if you had an argument that had something maybe like.
Wait, you said P is greater than 0?
Yeah. For an example, if this one said less than or equal to, then we would have to make sure that 4y minus 10 was greater than or equal to 0. You'd have to check that. And you'd also have to check y minus 1 greater than 0. So we just can't say 0 in this case. In this case, you would say y has to be greater than or equal to add 10. Maybe I better show my work. So if you add 10, you get this. And then if you divide by 4, 10 divided by 4 is 5/2. So that's going to be part of the answer. Instead of saying y is greater than 0, y is now greater than or equal to 5/2. I don't know who was here, who was gone, whatever, I don't know. But we did talk about that and show an example because I know that Landon said, well, why isn't it just always 0? And it's because this argument right there has to be greater than 0. I guess you could kind of say it's like the factoring ones that we talk about. If I tell you that y minus 2 or y, whoops, let's say 3y plus 4 is equal to 0. Then you have to do more than just say this is 0. All right, so you can pass those in now. Equal log base 3 of 9 plus log base 3 of 81. I want to know, do those two equal each other?
No. Yeah. I get my calculator.
Well, that's what I see some of you doing. You're going to your calculator. So go to your calculator, see if it's true, and then I'm going to show you why it is or is not true. But this leads us to a property of logs, probably one you will definitely see on your ACT. You don't try putting it in as an equation. You want to solve this part right here and find out what the value of that is, and then solve this right here and find out what the value is.
Yes.
So I will tell you, they do happen to be equal to each other. If we were to just manipulate, so I'm just going to work with one side of the equation at a time. If I were to work with the left-hand side of the equation, how can I figure out what log base 3 of 9 times 81 is? I would hope nobody would say that 9 times 81 is 729 and then try to change that into a different base. Yeah, you had your calculators, you were looking at that sum. But why can't we just say this is going to be log base 3? What's 9 the same thing as? 3 to the second power. And 81 is the same thing as 3 to the fourth power. So this problem could be written as log base 3 of 3 to what power? To the 6. When you multiply like bases, you add the exponents. I could change that. I could say, well, let's change that and say that that's the same thing as 3 to the 2 plus 4 power. You add those exponents. So log base 3 of 3 to the 6. Now, what is this asking for? It's a logarithm format, so what are you looking for? Exponent. So it's saying 3 to what power equals 3 to the 6th? And the answer is just 6. So the left-hand side of the equation simplifies to 6. If we talk about the right-hand side of the equation, you have to look at them as separate terms. This right here. That right there. Just the blue part is saying this. 3 to what power is equal to 9? 2. So just log base 3 of 9 has a value of 2. If you look at the next one, that's saying 3 to what power equals 81? And you get 4. You are adding those two together. So 2 plus 4 is 6, and that equals what was on the other side. So that is true when we look at that particular statement. That leads you into a property of logs. The property of logs says that if you are adding two logs together that are in the same base, what do you think you do to those arguments? Multiply them, and you can write them as one log. Or vice versa, if you are multiplying an argument, you can separate it into two logarithmic equations. So here's what we can talk about as far as properties of logarithms. Logarithms, as we mentioned in the bell ringer, is they're just exponents. So the properties of logarithms can be the same as properties for exponents. So here's what we have. The logarithm of a product, such as mn right there, the logarithm of a product is the sum of the logarithm of the factors. So the example we had 9 times 8 right here, or 9 times 81, bad color choice. So we had 9 times 81. The logarithm of the product is the same as the sum of the logarithm of the factors. Property you can use. What do you think would happen if I had division there? What would be the property? When you divide, you subtract the exponents. Yep. Same thing. So here's another way they can express it. Or prove that this is true. Let b of x equal m and b of y equal n. Then x is equal to log base b of m and y is equal to log base b of n. All I've done is I changed this exponential format, changed that exponential into a log format. You guys did that a couple of weeks ago. Change this exponential format into a log format. So if I were to give you this, b to the x times b to the y. Well, b to the x is m, b to the y is n. That's a true statement. Would you agree with that? Yeah? Okay. So if I am given that right there, the next thing you can do with it is we can change it into some logarithmic formats because we know what they are equal to. To do that, I'm going to work with just the left-hand side. What do you know about b to the x and b to the y? That's the same thing as b to the x plus y power. Just adding the exponents together. Are we okay with that step? Yes. All right. Let's look at some logarithmic formats then. One thing we know is true is I can take the log base b of both sides. I'm going to let that be my answers to a log problem. Change both to log base b. And I get that right there. So I just took the log of both sides. What you do to one side, you have to do to the other side. Where can we go from there? Well, what is the answer to this side right here? B to what power equals b to the x plus y? This is just x plus y. Proofs. Yeah. Great proofs. All right, now if I look at x, what is x the same thing as? X is the same thing as? The x is the same thing as log base b of m. I'm going to add to that y. What is y the same thing as? Log base b of n. And that is equal to, I can't do it from there, log base b of m. And there's your proof. That's why it's true. You will see logs in, no, I have not worked with logs in calculus, but yes, you can work with logs. We do. I have worked with logs in calculus. We do not here. We do not work with it here. So here we go. Here's an example. Use log base 2 of 3, which is approximately equal to 1.5850, to approximate the value of log base 2 of 48. Before they had calculators, they used to use these tables before the calculators were programmed to do this. So one thing I need to think of is what we need to think about getting this into a format that we can use. 48. Think of ways you can break 48 into factors. What are factors of 48? What are factors of 48? 2. How many times? You sure? 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32 times 2 is 64. So 2 doesn't work. 4. 3. No. Think about this. 48. What's 48 break down into? What do you think of when you hear 48? 12 and 4. What else? What? 8 and 6. Let's think about that one for a second. 8 and 6. What is 6 the same thing as? 6 is the same thing as 2 times 3, right? And 8 is the same thing as 2 times 2 times 2. So is 48 the same thing as 2 to the 4th times 3? You would agree with that. So I can take this log base 2 of 48, and I can write it as log base 2 of 2 to the 4th times 3. Now, why would I want to do that? Why did I pick 3 as one of the factors? Because of what we have right there. So we can change this into a log. When you multiply, when you have a product there, what did it say you could do to that? Write it as log base 2 of what? 3 plus log base 2 of 2 to the 4th. Now, what did this have a value of right there? Yeah, log base 2 of 3 had that value right there of 1.5850. What does this have a value of? No. What is it? It's saying 2 to what power equals 2 to the 4th? That's just 4. Remember, exponential format, 2 to what power equals 2 to the 4th? That's just 4. That's a nice 4 right there. So what does log base 2 of 48 have a value of? Did you type it in on your calculator to see? It should be that value. If those of you that were gone need to find me, I will be here after school for a little bit. Yep, see you later. Have a